Another common problem that causes a program become memory intensive is that the memory access is repeated. So using LDS can help us avoid those repeated memory access. So in this video, we're going to see one more example, that is matrix multiplication, and see how we can reduce the memory access using LDS. So with matrix multiplication, we have also seen this common naive implementation before. Within this matrix multiplication, we have one input matrix that is m by k, and the other matrix is k by n, and the output matrix is m by n. For each thread, we can simply calculate one output point in the m by n matrix. So here, we calculate the global ID x, global ID y, and if these global IDs are within this output matrix, then we start to calculate the accumulated sum. Our innermost for loop will iterate k times, and take k numbers from A and take k numbers from B, and perform an element-wise multiplication and sum them together. Eventually, we store the sum to the output matrix. So our question is, if we see some performance issue, the first thing we may guess is that some memory access is not coalesced. So which memory access is not coalesced? So let's look at the matrix multiplication process. And let's look at what the next thread, what the adjacent thread is accessing. For the input matrix A, that is my m by k matrix, they're accessing exactly the same data, so of course the data is coalesced. For matrix B, k by n matrix, the adjacent thread is actually accessing adjacent data that is on another column, so it is still coalesced. For the output, we can see GIDX plus 1 that is on the next column is also coalesced. So all the data are coalesced, so we don't have a memory coalescing issue. So let's try to dive deeper into how memory access works in this case. We have three matrices. Let's say for one wavefront that is processing this type of data, what the wavefronts are accessing. Let's say in the first iteration, this tile is accessing this piece of data in the A matrix and this piece of data in the B matrix. Then next, we move on. We slide to the right in the A matrix and we slide down in the B matrix. As you can see, the second iteration is actually reloading a lot of data from the first iteration. This data reloading may fall in L1 cache or may not fall in L1 cache. It's hard to say, it depends on the L1 cache size and the amount of thread that's running in the GPUs. So we want to come up with a solution. We know this tile and this tile accumulates to the tile in the output matrix, but then can we move to the next location without just sliding by one element? And if we can do that, that means we do not have reloading. And using LDS can actually help us achieve this goal. How can we achieve this goal? So let's look at the tiling code that is implemented for matrix multiplication. We define two tiles. One tile is for matrix A and one tile is for matrix B. We have four indices. One is BX, BY, those are block indices, and TX, TY are thread indices within the block. And we can calculate the row ID and the column ID of the thread in the output matrix. Then we have the loop. How many iterations we want to run? We don't want to run k iterations. We only want to run k divided by tile size. Of course, here we need to do a round up operation, that is the k minus 1 divided by tile size plus 1 comes from. We're just doing a round up operation here. We have two if cases. Those are boundary checks. We don't want to load the data outside this matrix. We only load the data within the matrix to the LDS. If it's outside the matrix, we fill in with 0. Here we also have two indices. One is current L and one is current right. The current L is the index in matrix A and current R is the index in matrix B. You can pause the video for a few seconds and try to understand how this calculation is done. Then, after a barrier operation, we perform this accumulation. How many times we need to accumulate? We accumulate tile size times. Then we think threads. Then we perform this barrier operation to guarantee that all the threads has calculated the accumulated sum. Remember, since this is implementing a loop, then we come back to the beginning of this loop. By moving this block to the right and to the bottom, we load another tile of data and perform this tiling operation. And finally, at the end, once we calculated the sum, we store it to the output matrix. So let's compare the performance. We have tried 3 different ways to implement this code, and we run on a single MI50 GPUs, where M and K are all equals to 8192, that's 8K matrices. And we tried 3 implementation, a naive implementation, where execution time is 1.6 seconds, or tiling implementation is 0.76 second time. As you can see, by applying this tiling operation, we can improve the performance by almost 2 times. As you can also see here, we also tried the ROC Blast implementation, which we will introduce in a later video. Our ROC Blast is implemented by AMD engineers in assembly. It's highly optimized, so there are a lot of other performance optimization mechanisms. It's a long-time research done by many talented engineers. So as you can see, for customized kernels, we can improve the performance by applying some commonly used methods, but still we cannot compete with a highly optimized code. So the takeaway here is that when you're running some mature workload, like matrix transpose and matrix multiplication, definitely try to use libraries like ROC Blast. But if you are not running some well-established algorithms, definitely try to consider using LDS to reduce your memory access, or convert non-collapsible memory access to collapsible memory access.